Hello and welcome to Rudy's Electronics Lab. And today I'm going to do a second episode on the Anritsu Vector Signal Generator that I got right over here. And I already did an episode on this one. And in that first episode I talked about how you can use it as a standalone device. I talked of the specifications. I've been comparing to a couple of other options for vector signal generating. I talked of things like the I/O connectors, the use of the memory card, and quite extensively I looked at built-in waveforms, and we also show them on the spectrum analyzer and combining them. Now for today's second episode, I want to dig a bit deeper into the device and I actually want to talk about all three different usage modes. So not only playing pre-recorded waveforms, but particularly the way you can use it when you connect it up to a computer, and then you get like a whole lot of new possibilities. We'll have to talk also a little bit about the way licenses work on this device, dig a little bit more into the samples and the sample and data structure. And I'll also tell you a little bit how you can generate actually clock signals, because that's a bit of an apparent limitation with the device. And we're also going to do some hands-on experiments. We're actually going to look at some QAM signals, and I'm going to show you how you can actually see these QAM signals, their constellation diagram on a oscilloscope using a bit of tricks. But let's start from the start. And let's remind us again quickly of the block diagram of the device. This is a sample player, you could say. So we got a sample coming up from a hard disk, which is loaded into memory. That's memory A and a memory B. Playing from these memories can happen at the same time, or you just play one of them. You can change the amplitude of it. You can change the relative delay. You can do a frequency offset of them. They're going to be combined, and then they're basically sent to the RF generator in the device. And you can also kind of take out the IQ signal or connect other IQ signals into the RF modulator. Now, this whole structure is basically pretty well reflected when we look at the screen of the device. Simple as the screen of the device might look like, we actually see in a very rudimental way the way that the device is configured at the lower half of the screen print I'm showing you here. And actually you also get to see additional information with each waveform. There is, or you can create yourself, up to 3 lines of text, which is super useful just to remind, things about sampling rate or particular settings of the waveforms that you have selected. Now, what type of samples does this device play? This is often not so easy to find out in specification, and that's not only the case for Anritsu, also in the various Roden and Schwartz and other devices I have. It took me quite a bit of time actually to find out what is the sample depth of the files that are being played. But on this Anritsu, actually it is 14 bits. So we can take like a bit more than 60,000 discrete values. Now there are later versions of this device, and these later versions sometimes have 15 or 16 bits of resolution, so a higher resolution. Still, I kind of like this device with only 14 bits. And why is that? Because in the sample memory, those 2 remaining bits are used for other functionalities. They are used basically to store marker information and to store information about whether the RF amplifier is on or off, so the RF gate. And this is super useful. They come with a number of predetermined waveforms, but you can also program that in your own waveforms. And I think I value the ability to create such markers along my own files much more than actually the 16-bit resolution, which I haven't been really missing up to now. But maybe your mileage varies and maybe you really need those 16 bits. But I really like this idea about these markers, and yeah, they take up space in memory, and that's the way they did up. Each word in the memory of 16 bits is 14 bits for the actual waveform data and 2 bits for the markers and the RF gate. Later I'll show you a little bit, if you create your own waveform files, how you can use those markers. Now, then we also need to understand a little bit of the data structure, because that data obviously is going to be stored in some way, and if we work at a computer, it's files being transmitted, exchanged between the devices. Basically, there are 3 types of files here. There is the waveform data file, a binary file, that is in its in a proprietary format. But don't worry, I'll show you later that you can basically import any type of your own data into the computer software and we transfer it into this waveform data file. There is the waveform information file, and that contains additional information about the whole settings of the device around the waveform. So like the sample frequency for which the file was designed, some output level and other relevant stuff. It's a readable file in text format. And finally there's a combination file, and the combination file basically can contain settings about multiple waveform files that can be sent, for example, at the same time to memory A and memory B and being played at the same time. And it can also contain sequences of waveforms, different waveforms or waveforms, for example, with different levels. So you can create a whole sequence type of thing without having to create a ridiculously long type of waveform file, but you can basically have smaller files and have the combination file basically defining how they follow up to each other. These files are being transferred from the computer to the device using FTP, and that is super convenient. You can also just go with your own FTP program to the device, see anything that's on the drive, etc. You have to get to know it a little bit. You have to know, for example, that specific file for specific waveforms have to go in the right folders or directory, and sometimes the naming matters a little bit, but now I'm already running into details. The whole fact that you can just easily access the whole device via FTP and all communication from computer to device goes via FTP is actually super powerful and makes you less dependent basically on specific software if in the future that would no longer be available, for example. Now let's do a quick hands-on test so we see how the software works and also how it communicates with the device. So starting with the device, if we want to use the computer software, we would typically go to utility mode, we would go to network setup, and there basically we would first check the IP address that is allocated to the device. When I started it up, it automatically allocated the IP address 192.168.1.217, so we'll need to remember that. Okay. And then what is also relevant, because we're going to use FTP, is that there is a user ID and a password. I'll quickly look at that because actually in the beginning when I first got my device I had a bit of a problem because I didn't know what the password was that the previous user has used, but I can simply overwrite it. That is not so easy in the sense that we don't have a USB keyboard or so we have to do it somehow with this interface. But you can actually use the backspace button to go back here. In the regular way you would set something a password. If you make it too small, then you would get because then we have to do the end button, and let me see to get to the end. Okay, we've got the end button here. The very Japanese message, too fewer string. So clearly the device is not happy here. So let me try once more, and I'm going to set a password by 1, 2, 3, 4, 5, 6, 7, 8 times the capital A, and it actually starts right away at the beginning again. Now I will go back to this end button again and I'll set it. So now I think I got my password properly set to 8 times capital A. Now that's it for the time being. Let's go and see the software. So this is my computer. You need Microsoft Windows. We got the IQproducer software here. Not exactly the highest graphical resolution for the icon, I would say, but once we started it actually looks kind of cool. And it asks us which instrument we have, and that is relevant because then it will prepare the data files exactly fitting the instruments. You can also later change that. I start it up, and basically we see here a screen where we can select different type of cellular protocols and go into details. Same thing for non-cellular protocols, something which is called generic purpose here, and a category of simulation and utility. I'll get back to that later on. Now, so how does it kind of work? So if in, for example, cellular standards, we would go to a standard. Let's take the 3G wideband CDMA communication standards, and we would go there, and then we get all type of settings that we can do that relate basically to that, including a number of submenus and channel edits. You can do that. It is quite extensive, I would say. And if you would choose another protocol, like for example the 4G LTE standard,
let's take the frequency division multiplex version of it. Again, you see a completely different screen here with all types of settings for reference signals, for subframes, and what it be. There's an easy setup as well. Let me see. Oh, then we can directly set kind of some standard type of things. I'm going to close this as well. And so what I'm actually going to do, I'm going to go to a television standard. I'm going to go to the DVB standard, and I can choose between a terrestrial and a handheld version. Let's take the handheld version. We can see here it generates some data in there. So you got a pseudo random code, PN15 code, for example, going over it. Lots of settings I'm not going to go into right now, but I just want to see how this actually going to communicate with the computer. And to do so, you use the transfer and setting wizard. So there's going to ask again what a target instrument is. Two different versions being offered. We got the right IP address already here. The machine, by the way, will just remember the IP address and the password. I just set the password to show you how that works. I'm not sure I got the right one here, so I'm just going to do the 1, 2, 3, 4, 5, 6, 7, 8A, FTP port 21, and off we go. Yeah, and we do see basically that the device is being recognized. I can basically tell him that to create a waveform file, to put it in a package which is called multi-carrier. That's it, multi-carrier. I can even tell the device to directly load it into the system memory. But I'll not do that here right now, because I want to show you basically how you would do that all by yourself. So you would do transfer. Now we're going to go to the device, to the baseband unit. We're going to tell them to load a file to the memory. You have to select the package, and we were just told that is multi-waveform. Well, there are a whole lot of packages right now on my device. Yeah, multi-carrier, sorry, that was the right name. Package list and multi-purpose, and that is what I've just generated here. So I'm going to load this one. That's it. I can leave this menu. So it's in the memory, and now I basically have to bring it here to the pattern. I go to multi-carrier, multi-purpose, and there we go, and the unit starts playing it right away. Again, in the software I could already have instructed here to skip that particular step here, so directly goes into the memory, but that's the way you would do it by hand to find the waveform which has been already saved at an earlier point in time on the device. What I also wanted to show is that you can just also go to the device with any FTP client. So I'm just taking here an FTP client on the Mac. I've typed the right host address. The username is MG3700. The password is AA23456778. Port number is 21. And now we basically see, yeah, right away it logs into my remote device here, and I see both the card slot and the hard disk. So on the card slot, I see anything coming up that's on the card. On the hard disk, I get to see the whole hard disk. Here are the packages that I earlier saved some information in, so I can open it. So as you might remember, it was the package like multi-carrier, and there we go, multi-carrier, and this is the file we just created. I see here that the date tag is slightly off, like a day minus a couple of hours. I don't know exactly where is that, because the MG is at the right date. Maybe one of my other devices, maybe my Windows computer was at the wrong date. I don't know. But this is super convenient that you can just go to any point in the device in its storage and basically use FTP, directly move files around and whatever you need to do.
Now, I'm getting to the core part now, and that is about the 3 different use modes of the device. First of all, it can be used as a standalone device, and then we're basically playing information which is already available on the hard disk inside. And that's basically what I've already been looking at in my first episode. Secondly, the device can basically be used together with a computer, and the computer can then generate waveform for you. It can be according a specific technical standard or so, specifications, but it can also be more generic type of waveform. And that piece of software is called IQproducer. It's available for free. It's actually still being updated because also newer Anritsu devices use this software, so that's very nice. And the third usage mode is basically when you want to create your own files with other software, and that can be MATLAB or Python code. It can even be Excel. I actually use all three of them in conjunction with the device. It all works, but the basic example I'm going to give you today is by Excel. That's the most easy, I think, to demonstrate, because it's just easy to see the file format. That goes into IQproducer and then to the device. Now, talk about all these three usage modes one by one, starting off, of course, with the playing of the pre-installed waveforms. And as you see on the screen here already, there are a lot of them. There are almost 400 waveforms already as a standard on the device. And what type of waveforms are these pre-installed waveforms? Here you got an overview of those waveforms that are already on the device, regardless of what type of additional licenses you might have. So there are a bunch of waveforms for cellular standards, 2G, 3G, even 4G standards. So it's actually pretty decent to have 4G standards on such a device. Then non-cellular standards like broadcast standards for video signal, for television. There's some cordless telephony, the Japanese version at least. Bluetooth, some very specific Japanese standard for telemetrics. There's Wi-Fi standards there. Interesting, both ODFM and other modulation method, if I remember well. There's some GPS satellite stuff. There are some noise waveforms and some other specific waveforms. I'm not going to go in details here. As I said, this is all already available if you don't have any additional licenses. With additional licenses, there are a couple of additional waveforms like WiMAX and radar patterns and a couple of more specific Japanese standards. Now these standards are, of course, created completely complying a technical standard, and it's very detailed how they have done that. There's literally hundreds of pages of specifications and parameters. It's super well documented, not only in the brochure but also in the specific manuals that come with it. And I'm just showing you now here a picture how you see how such a waveform basically is complying with the standards and the way that the data is built up here in specific type of standards. This is just as an illustration, and here you even see a more complex illustration of a US CDMA standard. So the documentation is excellent, I think, in this regard, and that really gives confidence that these standards are really implemented in this device, that is completely compliant to the standard, and also which version of the standard and what all the choices that have been made basically. And later I'll show you also, when you talk about generating your own waveform, that you can actually change all type of stuff about that. Now let's go to the second usage mode, and that is generating your own waveforms. And like I already said, this can be both based on technical standard, but then you can set all your own parameters, or you can create more generic type of waveforms yourself. So let's go and take a quick look at that as well. Now again, here you see an overview of what type of waveforms can be generated by the software. So this is a different table than the table you saw before, although we see the same kind of overall categories. We see cellular standards, a number of non-cellular standards including broadcast, and then we also see the general purpose type of settings with which we can create waveforms, like more general modulation methods or whatever. Now you also see here that you do need licenses in a number of cases in order to generate these waveforms. Most importantly, the generic purpose things, TDMA, the noise generator, those you don't need license, and that's what I probably most care about. And interestingly enough, the multi-carrier waveform generation, the manual says that you need a license, but actually I don't seem to have that license, but it runs nevertheless, so I can't fully explain that. There's a bit of a discrepancy, I think, between the manual and what actually works and doesn't work on the device. Okay, this is a little post-recording update on these licenses. I stand corrected when it comes to the
the multi-carrier license, because I checked it out once more and there is a multi-carrier license on my device. So that kind of explains it. At the same time, I still find the licensing situation kind of confusing, because according the manual and the brochures, the LTE license is a paid license, but here it's on my device with serial number 1, so it doesn't seem to be a paid license. And the TDMA license, that is I think the one for any generic type of waveform as well, is supposed to be a standard license on any device, but here I see it with something with a license number, almost thinking that this is a paid license. So yeah, still not entirely sure about the whole licensing situation.
I showed you a table before of built-in waveforms, and I'm now showing you a table of waveform from the software. How does that relate to each other? I try to make an overview table here that has both of the categories there. I'll post them somewhere on my website, and you see they're kind of complementary. It's not exactly the same waveform. Some of them are available as pre-recorded, some of them are available for constructing your own with your own parameters in IQproducer. Actually, you have to go into a lot of details actually to find out exactly which licenses are needed and how it works together. I'm not going to go in great detail here, but I wasn't able to figure everything out exactly when it comes to this, the possibilities and the licenses. I can just surely observe what's on my own device at least. And talking now of licenses, it's kind of important to understand then how that whole thing about licenses work. I mean, licenses are not unusual. I think almost every manufacturer now has this type of business model with licenses. I think Anritsu is unusually generous in the sense of how much things you already can do without additional licenses, and I really applaud the device for that. However, if you want to use stuff with licenses, you need to understand a little bit how that works. So the thing is that the licenses are being installed and checked by the device. So that basically means that on the computer software you can generate whatever software, whether you got a license or not. I got a little asterisk here because actually some specific one were missing. I don't really get it. But Lars and beyond, you can do everything already on your computer. Then you move them basically to your device, and then your device basically finds out whether there's a license for it or perhaps not a license for it, and then it will not play back that particular waveform. So it's a well, I don't know, peculiar way this is implemented. Well, maybe not peculiar, but this you have to understand more or less to make good use of the device. Now, digging right into the interesting type of waveforms, I will start with kind of generic type of waveforms using different types of modulation methods. So if you want, you can just make like a continuous stream of that type of data without any time frames or other structures, etc. You can do that, but you don't have to. And I'm here just to give you an example, for example, of 64 QAM. This is where you generate such signals. It's all built in, it works well out of the box, but if you want, you can edit quite a lot of it. You can, for example, change the whole mapping of each value to a specific dot in the constellation diagram. You can play around with oversampling, other types of things. It's really fairly flexible, even alone if you look at the modulation method in itself. And 64 QAM is just one of the many type of waveforms supported by the device. Actually, I tried to make a bit of an overview, and these are all waveforms here. I sorted them a little bit that the device supports. These are actually screenshots from the computer software, and I really like the way the computer software already gives you a bit of a preview of the kind of constellation diagram or the values that your modulation method can take. And like you saw earlier with the example of 64 QAM, some of them have a number of different settings with it, and in the next sheet I'm basically showing a number of these settings where they are available. Some of them allow for some type of rotation, some have frequency deviation, some allow you to map the different values to a file with all the mappings or manually, etc. So very flexible indeed. Now, I've been talking long enough. Let's take a look a little bit at the instrument, and the demonstration that I want to give right now is look at one of these more complex waveforms. I'm going to look at the 16 QAM signal, but I'm also not only want to look at the Anritsu in itself, how we place back that wave file, but particularly want to look also into how we can observe such a waveform on the oscilloscope. And we're going to use a little bit of a trick, a little bit of an undocumented feature on the oscilloscope that we'll be using in a moment, so we can actually go and see that particular waveform. So let's go and take a look at that. I would now like to guide you a little bit through the process, how we can actually use a oscilloscope here to look at the constellation diagram of IQ signals. And I'm using here the Roden & Schwarz 2004 because that oscilloscope allows, has a blanking function. Actually, it's not a documented function, but you can turn it on. And I'll show you in a moment how we're going to do that. So in order to do this demonstration, I have uploaded a 16 QAM signal that I made myself with the IQproducer program. And right now we see it here on the screen. And as you already might kind of see, there are 4 distinct levels, both for the I and the Q signal. I'm not even sure they're on the straight line, but we can kind of distinguish 2 signals. I'm going to turn off one of the channels, so we just got channel A here. Now, depending on the synchronization that we have here, I'm actually going to use a little bit of persistence here. Yeah, that's how I like it. We can see kind of these levels coming in, and we can see the periodic character of the waveform. Now, so what we need to do basically is to tell the oscilloscope only to look at the particular point in time that we're interested here in observing the signal, when we feel that the IQ signals are the moment they should be sampled to know what their value are. So it's somewhere on this waveform, maybe not exactly on these tops, maybe somewhere else, but we're going to try to find out. Now, what can we, how can we design that process? In the way that I created the signal here, it automatically comes with a signal clock, which comes out of the back of the device here on the AUX3 connector. So let me look at that. I brought that signal here to one of the logic channels of the scope. And somehow I want to use this symbol clock here to determine the moment, but I cannot use these here as a blanking signal. This is way too wide. I need a very short blanking pulse basically to do this process. Now, in order to do that, I'll be using my my signal generator here. This is a signal generator, and I'm using here basically I think it's called the gate function. So actually it created the pulse. The pulse is triggered by an external input, which is the word clock here, and I can set the width of the pulse, I can set the amplitude of the pulse, but I can also set the delay of the pulse. And I think this is easy to show if I just put this waveform right a little bit out of the way and look here at the pulse that's already pre-configured here. You can see here there's a little pulse. I can make it a little bit larger, a little bit down, and now I've been setting this pulse halfway these blocks here, but I basically can move them around. Now, so let me activate again a signal here. Let me move it down a little bit. So the pulse is now set that it's at the top here of these signals, but I can move it around. Let me just see. Can you see that here? This is the delay setting here, and I can move the pulse basically to different positions. So later we're going to find out what the optimum position is. We'll do that a little bit with trial and error. But I think this is about the moment that we want to go to the XY mode. Let me first turn persistence off again. There we go. We turn the device into the X and Y mode. And there we go. And in order to use this XY mode in blanking, as I said, we have to use this undocumented command. And I'll be showing it on the screen now. It's actually quite simple. Using the remote interface, you basically tell the device to activate the blanking mode, analog blanking mode. There's also a digital blanking mode. And you also tell the device that channel 4 is going to be the blanking input for the device. Okay, let me kind of put both of the signals on.
Let me take this signal and move it a little bit to the middle of the diagram. Yeah, that's kind of okay. And now basically we don't see any blanking going on yet. And in order to see the blanking, I will need to reduce the waveform a little bit. I think 79% is going to be okay. And I'm going to use this channel 4 for blanking. I have to put it to quite extreme position, channel 4. It has to go into overload a bit, I'm afraid. But I've been experimenting a little bit with it, and that's actually the way to go. If I do this and I take my vertical position to a low value, yeah, there we basically, it's a little bit experimenting around. There we actually see it coming. I already see a little bit what seems to be a constellation diagram, but it's not perfect yet on the spot. So let me play around a little bit with the delay here. Now we seem to be getting a little bit closer. Let me go into the fine setting. Now this already seems to be a little bit more what looks like a constellation diagram. But let me put it like this. Yeah, I moved the button around a little bit more, and now I think we got more or less the diagram that we're looking for. Here we see jumping basically from one position to the other. And when I increase the time here, so I'm capturing more periods basically, I quite clearly see the diagram coming in. Let me put the background waveform a little bit lower. Yeah, now here we can observe basically the constellation points. Yeah, now we're zoomed in a little bit more, and again we can see the constellation point. I can look at a bit of a slow thing, and we can see how basically the signal move from one constellation point to the other. Again, I can make that a little bit more or less visible by basically playing around here with the waveform brightness. And depending on what I'm catching up here we get a nice constellation diagram. Using the same methodology as we have here for the 16 QAM diagram, we can of course also look at other constellations. So I'll now move here on the Anritsu to a 32 QAM. Let's confirm that. There we go. Yeah, and you see 32 QAM where the outer points are missing according to this protocol, and even going to higher modulation standards like 64 QAM, and I'm selecting that one right now. Yeah, so here we see the constellation diagram for 64 QAM with 8 discrete values on the y-axis and 8 discrete values on the q-axis.
Now we've just seen a demonstration of a particular type of waveform, and in that waveform it was actually a waveform generated in the way that I just explained. In that waveform there was actually some clock data present. That was the data I was basically using, for syncing of the oscilloscope. Now there might be some cases in which this clock data is not present as a marker, as it was in the previous example, and there we run into what I find to be a rather peculiar type of limitation of the device. I don't see any clock out. I don't really understand why it's not there. I mean, I see it on other devices, and that would be exactly what you would expect, like the sample clock out coming out of the device. But the sample clock doesn't come out of the device, and that is really a limitation, I think, in general type of use. So as long as you don't have that already programmed into your markers, or will program into your markers yourself, the device itself will not generate or offer you these the clock signal. Can that be overcome? Yes, it can quite easily be overcome with a little trick, I would say, because what we would do is actually use the external sample clock input. So basically you wouldn't use the internal clock of the device, but you would use a separate device like a function generator or whatever, input into the device and take that signal as a sample clock instead of the built-in sample clock. And that way you can actually, of course, take right away the signal that you generate yourself, and you got exactly that sample clock that you're looking for. But there's a little bit a route around it. Then you also need to be aware that in order to do so, you can basically run any sample clock all the way up to 160 megahertz, which is the max of the device, but the physical incoming signals are to a maximum of 40 megahertz only. And after that you have to put a multiplier, and you can also put a divider if you wish. And I'm showing you here the table how that kind of works. That can be kind of convenient because this means you can also use a signal generator that only runs until 20 or 40 megahertz and even create faster signals. But then again, you might not have exactly those signal pulses that you're looking for. So at these high speeds, above 40 megahertz, this is something that you have to take into account when you use the device. So with this workaround you kind of can get there, but again, I don't really see why a clock out or word out, if you wish, for the whole word in case of a more complex constellation, while it's not, or symbol out if you want to call it, is not, it's not available on the device. Now we can't look into each individual option being offered by the device, but let me pick out a couple of them, and one of them is multitone generation. So here basically we can generate our own signal made out of multiple carriers. I think there can be dozens, if not 100 of them, etc. We can create them by hand, giving them all a frequency and an amplitude. We can also have it itself generating via kind of a wizard tool the type of signals that we're looking at. So we could generate, for example, a signal that looks like a OFDM type of signal. We can take carriers out, for example. Sometimes it's done in systems that are prone to sometimes interference. They would have specific carriers being taken out of it, etc. And all of this again you can do with the software that comes with the device and that is available for free. Another thing that is quite useful in that context, and I'm going to show you now, but you can basically do it anywhere, for all of the signals that you generate, regardless if it's standards or complex waveforms or multi-carrier waveforms, you can do a time domain preview where you can see how that signal looks in the time domain. It does have its limitations a little bit in terms of settings and resolution, but it's still a rather flexible tool. You can even just give him a waveform and say, show me the time domain for that waveform. So you don't necessarily have to connect up an oscilloscope basically to be able to get that time domain information. You can preview it basically on the computer software itself. And in a similar way you can also look at the frequency domain preview, so you don't need the spectrum analyzer basically to investigate the waveform that will come out of it. And again, in a similar way you can also do a power domain analysis, just again on any type of waveform that the software is being able to generate. Now I've tried to cover at least a part of the way of generating your own waveforms within the device. There's much more to tell. You can also do a lot of things like generating things with slots and frames and a lot of things more. There are countless number of settings here, but I think it goes out of the scope of this episode to go down there. And let's move right on and going to look at how this device is actually used at the moment that we want to use our own data coming from other devices, from other computer software. And like I said, it can be any piece of software, more specifically any piece of software that can generate a plain data file with values in an ASCII separated file type of format. There are actually multiple ways that you can feed it in. There are multiple definitions of this separated values, depending if you want just a waveform and a separate file for markers or all combined in one file. But it's all super simple really. I mean, it's very easy to do. So how does that kind of look like? I'm going to show that with a little example that I tried myself, and in the most simple form basically I'm creating here a set of two waveforms. I'm creating a sine and a cosine waveform, and I want to play them back basically from the sample memory of the device as a I and a Q. No, not vector, they form together a vector, of course, I and a Q value. So I simply took Microsoft Excel here as a demonstration. I calculated these values. I created here, I think, 1,000 values. I plotted them here on a little plot as well, and that will simply go into the device in a moment and being played back. And as you see here also shaded in yellow, I also created here some markers. So I decided to make a marker that marks like the beginning of the sequence, so I got a kind of a frame start, if you want to call it that way. I also created a little bit longer thing for the frame start, a bit of a longer pulse, and I create another marker that can serve as a kind of a clock signal if I don't use the external clock input, so it just goes on and off and on and off all the time. So I simply export the file, at least the values and the marker values, just with as a comma separated type of value file. Super simple to make. I go to the software of the Anritsu. I use waveform input, and here I can simply select my file, tell him at what sample frequency it's supposed to play back. I can do some other settings, even create something like frames and slots. I don't need all of that, etc. And that's about it. That's about everything you need to do basically to create your own waveform and play them back by the device. And again, because as I explained in my previous video, the device has a quite incredible range of when it comes to the sample playback frequency, etc. It really makes it a very versatile device. So you can really imagine, and I tried that also a little bit, of you using MATLAB, for example, and creating quite complex type of waveforms and bringing them into this device. Or doing that using some Python code. And I've seen some people doing that with success. Now with that I want to come to a kind of a final verdict about the Anritsu I have here. That doesn't mean that this is the last video. Actually there's some interesting stuff I hope to get into soon. But for the time being, kind of reviewing the device as such. Do I like it or not? Yeah, I like it a lot. I certainly don't regret my purchase. And what are the key advantages, I think, of this device? Well, first of it, it's the sample rate, the modulation bandwidth, and the memory. They're excellent, I think, if you compare it to other options that were available at the same time on the market when this was sold and are now available around this price bracket on the second-hand market. The fact that you can be playing two signals at the same time makes it very flexible. The amount of I/O that the device has is very strong. The markers that you can program make it powerful. I like the software support. It's still a regular software program, still being updated. It's available for free. The documentation is fantastic in most regards. I like the way FTP is being used basically on the device for moving all the files around instead of all type of proprietary stuff. And I also kind of like that the operating system is not residing on the hard disk. So if you ever have a hard disk failure, you could still kind of get another hard disk in, get it properly formatted, copy the waveforms from the Anritsu website or somewhere else, and you got a working device again. With a lot of other devices from this period and even now, the firmware basically, the OS resides on the hard disk. If something goes wrong there, you're doomed basically. And I also like that the hard disk is actually in the caddy on the back, so you can even just physically take it out easily. Of course, there are also a couple of disadvantages here. First, I'll mention the proprietary IQ connector. I looked at that in the first episode. Yeah, I really don't get it. Why don't you just put a number of B and C's there instead of people having to build their own connector? Yeah, the missing sample out, sample clock out, or also word or symbol. I showed you in this video kind of a workaround, but I really would have preferred if it's just right there on the device. And finally, small disadvantage, I would say the licensing and software situation sometimes is a bit ambiguous to me. Again, the device is very generous when it comes to what it can already do without licenses. When you do need licenses, sometimes I was a little bit confused. Some stuff that supposedly needs a license just works on my device without a license. Other stuff I should see in the IQproducer software, even if I don't have a license, but I didn't really find it. maybe I didn't find everything on exactly the place where I was looking for it, but I think overall the licensing situation is still a little bit complex and confusing. But having said that, I think these disadvantages are relatively minor, and I think this is really one of the worthwhile devices I think in my lab, and I can really recommend it to people that are looking for something in this type of price bracket, basically, to be able to generate high frequency modulator signals, and in particular vector or IQ types of signals. Well, I hope you like this video, and I hope to see you back soon with Rudy's Electronics Lab.